So today we will mostly talk about now optimization, but I just want to recap just a few things about human vision or computer vision. Mainly the stereo vision we talked about, when we have two cameras and then we can triangulate and see in 3D. And in fact, that's what's happening in our human eyes. So we have two eyes, and they have a baseline. I mean, the eyes are not at the same place, right? So there are two different places, so we can see and exactly see where the points are in 3D. So this is interesting because now when you close one eye, you still see, we are not like computers. We still see some 3D, right? So why do you think that's happening? I mean, have you tried closing one eye? I mean, it's slightly uncomfortable, but you still can recognize objects and 3D features and all things. So can you recognize 3 or 4 different cues? We call them cues, something that lets you know about. So visual cues for 3D means like it lets you know about the 3D. So for example, we learned camera projection, right? So the projection equation was something like the perspective projection equation was something like U equals to X by Z. So what does this mean? It's being scaled by Z, right? So the further the object is, this will be smaller. So the objects will be, this is obvious for us. But mathematically, you can see now that, the further the object is, they look smaller in the image. And that's one of the cues, like you can see the ships. Some of the ships are far away, and so they are higher in depth. They're further away. So this is the obvious cue from perspective projection. Can you guess other cues? What makes you see 3D? But that's already, right? The stereo vision is there. We studied about that. So apart from stereo vision, can you guess other things? Yeah, well, yes. Ground plane and foreground and these things are our object priors. Those are one cues because we recognize object. Even from just by looking at the image or photo, we recognize the object and we see like the shape has to be like this, right? So that's one thing. But just from the image, something that even a computer could see is what we play in, do in computer graphics. How many of you did computer graphics? Well, quite a lot. Okay. Did you have to apply lighting and shading and all these things? Why did you have to apply that? To get marks. So the reason is that 3D shapes, they reflect light differently, right? So you have to characterize that if you want to make a realistic image in computer graphics. So you have to model how the light is being reflected and how it's different at different sites. So in the other way, so computer graphics is the inverse of 3D vision in a way, because in computer graphics you are trying to render objects from 3D and make realistic images. And in 3D vision, you have real images, and you want to get very nice 3D models. So in computer vision, we use shading. So you see that this side of the, let me use the mouse. So this side is darker, and this side is bright, right? So it means that there is a change in surface orientation and the angle of the surface could be derived from this change in illumination. So the same in, everyone knows Mona Lisa, like the chicks, they're darker because of the reflectance of the light is lower there. So can you guess one more cue? One or two more? So you mean like, because it's like coming out, right? It looks like it's coming out of the picture. Like people do this with the Instagram filters or something like that. They make the pictures, the background blurred, and the face and the body like coming out. So this is we're trying to model focus here, right? So when you look, we focus at one point with our eyes, and the rest is blurry. So where you're focusing, that gives already a cue that the others have different depths than what is, very sharp and bright. So the blurry part should have different depth from the sharp part. So that's another. So there are also like more minor cues. For example, in this painting, you'll see that the ships are sort of fading away. They're like, so something like foggy or misty. So this is also a very common cue that we can easily use, but it would be very difficult for a computer to use that, to see the depth. So misty or fading away means that it's very far away in depth. So these are some of the visual cues you could use apart from this stereo vision to get 3D in let's say in a computer algorithm using artificial intelligence. So if you could train a model to predict depth using training labels. If it's a deep network, it could automatically look for these kind of cues. So that's a goal. So there was one paper in ECCB in a conference this year about depth prediction. So the colors here, so this is their method's depth. It's color coded, so different color means they're at different depth. So there's a car, I think it cannot play for some reason. Anyway, it's because I changed the computer. Anyway, you'll see later. So this is so this was unsupervised depth learning. Maybe I can just put it in YouTube. So if you're interested to work in 3D modeling or getting 3D shapes, there are lots of other technology you can use apart from vision itself to get 3D. So some of these things are actually based on stereo vision, but using different sensors. For example, how many of you know Kinect, the first one? So it's a depth sensor. It can detect depth at every pixel. But it was the first one was using a stereo vision method, but with IR rays projected on the outside. So it projected IR rays, which on one side, which acted as the first camera, and it had IR sensor on the other side. So the projector is kind of an inverse camera. So in that way, it was using stereo vision. Then there are other, so this one, this is a, oh, I didn't do slideshow. So this one is called time of flight sensor. So you show the sensor and the object, and then it emits light that is modulated. So when it returns back, it can detect the phase or the change in time, and use that to predict, to compute depth. So light travels at certain speed, even though it's very fast. So now we have like gigahertz, clock rates that can detect even small millimeter distances. So this is a new version. I think they're coming out this year. And this is the Oculus, the VR set. It has IR sensors, so it can like get the 3D shape of your face when you're using it. So imagine you're talking to someone else, so you could give a 3D feeling to the other person. So one more thing is we talked about last time is single value decomposition. And one thing I forgot to mention is what's the relation, what does it tell about rank of a matrix? So I will again use the board. So we have something like this in the decomposition. A is the matrix we want to decompose. It gives a set of orthogonal vectors, V, in a matrix, and the other set of orthogonal vectors, U sigma. So if you multiply U is the set of unit orthogonal vectors, and sigma is the scaling of these vectors. So it gives you a scaled set of orthogonal vectors, and V is unit orthogonal vector, set of orthogonal vectors. So what happens is if a matrix has certain rank, let's say rank is n, then you have these V columns. So let's say A has more columns than n. Let's say this is n plus 1. So when you project this vector, so this becomes 0, because the equivalent scaling for this will be 0 here. So what it means is that at the same time you are getting the kernel, because you have A times X equal to 0. So that's the kernel of A. And by looking at sigma, seeing which of the vectors are being scaled to 0, you also get the rank of the matrix. So the number of non-zero diagonal entries. So sigma is something like this, right? So you have A, B, let's say you have 0. It could be something like this, or 0, more. Not for this example, but so it has rank 2 because only 2 diagonal entries are non-zero. So you can get the rank of the matrix by just doing single value decomposition.